Hey there, welcome to another problem session. So today we're gonna examine this classic problem of one-dimensional case of elastic collision. So, there are quite a few ways of definition of elastic collision, but elastic collision is a collision in which, it's a elastic collision will be a collision in which when the particles hit each other, this strikes that, or maybe they hit each other, then if object A and B, their internal states do not change. So if you have just an elementary particle, then these particles remain the same, okay? So internal states don't change. So if this is before and this is after, then maybe this guy goes this way and this guy goes that way, whatever, but then this remains A and this remains B. Okay. Consider what will be inelastic. Will be a maximum inelastic will look like this, A and B, and maybe they just becomes one blob, some C. So this is inelastic. So this may go that way. Okay. It may be another more really another elastic will be is A and B, they hit, but what comes out is some kind of looks like A, but it's in it has internal structure like an atom and got excited to another state. So in quantum mechanics you have these atoms, can be like a silver atom. This is the state this was in, but then it looks like A, but you have some A star. So like this atom got excited. It's still silver, but it's this guy. So you have this much energy internally more. So you can't just have this guy. Let's say some B star. So you have a different, this one can be even B itself, and it didn't change this guy's state. So they look like A and B, but they're internally different. So this will be inelastic. So we're not going to address this. We're going to do this elastic collision. So what happens here if they remain the same? That means we didn't store any energy internally, which means everything is external. And so this is going to be, in this collision, of course, all collisions, you'll have a momentum conserved. But in this case, in elastic, you'll have also kinetic energy conserved. Kinetic energy before equals to kinetic energy after. This is total kinetic. So you'll have two conditions. This is condition every single momentum. But of course, you might say a third condition I want to say, total energy. This is going to be in all total energy before equals total energy after. Total energy after. So these guys, this guy and this guy is in every collision, but this guy is in an elastic collision. Now, when it's a total kinetic energy here, we are going to, in a non-relativistic, so kinetic energy in non-relativistic is just a formula half mv square, but kinetic energy relativistic is actually gamma u m0 some speed v v square m0's c square. Not even v part is kind of hidden inside here. So we just call this energy of a elementary particle. If particle is elementary, then this stuff doesn't happen if this particle is elementary. And so we always just think in terms of gamma m0 c square if it's elementary. If it's a composite particle, then you have to be careful whether it can get kicked up into higher internal states. And then you can say, oh, that much is so-called, you might say, as some sort of potential energy that has been stored. And so I have to take into account that energy. But if I don't have internal structure, then I just go with this energy, or relativistic energy. So kinetic energy is included into relative energy, and so you have a gamma v. If you say what happens when v is much less than c, then this turns into half m0 v square plus m0 c square, which we can ignore. This is constant, so it doesn't change. All right. So much for the background, and we want to do this both relativistically and non-relativistically and see what the differences are. Okay. Okay. So in a non-relativistic situation, we will have two conditions. One is momentum conservation, and another one will be kinetic energy conservation. Okay, so momentum conservation, if it's so in one dimension, one equation, in two dimension, two equations, etc. Okay, and this will be only one equation always, because this is scalar and this is vector. This is vector equation. So when do one along the x-axis, I will have I'm going to use rest mass notation. So if I say ma, this will be same with m of particle A, which is a rest mass. I'm not going to use this. This adding extra zero is too much. Okay. When we do relativity, we're going to make another simplification in our calculation. We'll set c speed of light equal to 1, and later on we're going to restore it in calculations. So these are some of the notations we're going to do later. All right. So here, this just along the x direction, ma vax plus mb vbx equals to ma vax prime plus mb vbx prime. So along the x-axis, and this equation then becomes ma, everything to the right here. So I'm just going to write in terms of these symbols that's given here, va plus 0 equals to ma va prime plus mb vb prime. So this is going to be my equation 1. Of course, this thing can be erased, right? So kinetic energy, this was going to be I'm just going to write half ma va square plus 0 equals half mb ma va prime square plus mb bb prime square. So this is number 2. So this is the standard way of doing this, and then you can do lots of algebra and solve for VA prime and VB prime. Okay, I'm going to show you another way of doing this problem. Instead of using this, I'm going to use symbols. Okay, so I'm going to use for momentum. So this one I'm going to just write down as PA, and this one I'm going to say PA prime, and this one I'm going to say plus PB prime. And you'll see in a minute, because these guys, so if you have MA VA square, you can see this one just be or half of this kinetic energy will be half PA square over MA. So it's kind of a little bit less writing. So this one actually half got cancelled, and this is a half here. Half got cancelled from every one of them, and so they have a PA square over MA equals PA prime square over MA plus PB prime square over MB. So it's a little less writing, and I'm gonna try to solve this. Solve for PA prime and PB prime. Okay. So now I can just, I want to solve for PA prime. Then I'll just substitute it here and see what happens. So that becomes PA square over MA equals PA prime square over MA plus 1 over MB, this will be MB, PA square minus 2PA PA prime plus PA prime square. So let's try to do, I'm going to change gear because I think it's a little bit better to substitute this. Okay, so when I substitute that, I'm going to have a PA square over MA equals to PB prime, PA minus PB prime square over MA plus PB prime square over MB. Okay, I think I like this better. So this just forget that step. Okay, now I expand this because I see that PA square on both sides will cancel out here, and nicely. It's going to be PA square over MA. So this will cancel that guy. Minus 2PA PB prime over MA plus PB prime square over MA. So this whole thing come from this plus PB prime square over MB. So this guy will combine and this guy will cancel. So this guy will cancel out, and this will be common between all of these guys. So this will become PB prime, and so this is 1 over MA plus 1 over MB times PB prime minus this 2 times PA over MA. And this whole thing has to be equal to 0. Now it's very easy to see. PB prime is either 0 or it's like it doesn't even see it, it just goes through. Okay, or PB prime is this whole thing. It's 2PA over MA over 1 over MA plus 1 over MB. So there are two choices here. and we should explore what those choices are. So if I have a choice of this, when this is the case, what happens? PA prime will become PA. Remember, PA equals PA prime plus PB prime. So from there, I plug in 0. So that means this just says particle A came in and B was at rest. So V was a 0 and this comes in with whatever V and this same particle. Then later on, B remains where it is and A just keeps going right through as if B didn't exist. So this one is a little bit unphysical, so we just ignore that. So this is ignore that. So PB prime is this. Then what is the PA prime? PA prime will be PA minus PB prime, and then just put it in there. So PA 1 minus 2 over MA 1 over MA plus 1 over MB, and that just PA times you get 1 over MA minus 1 over MB minus 1 over MA, because this will go have both of them, and 2 over MA will be more 1 over MA plus 1 over MB. You can simplify this more. So your PA times MA minus MB over MA plus MB. And if you write this guy, this will be PA times, it will go over there, 2 times MB over MA plus MB. So you've seen these answers. You say what's the speed, what is BN prime and B prime. From there you can immediately get what those things would be, right? So for instance, you can say VA prime will be PA prime over MA, and so you have this over here, and so this will cancel MA, and they're just going to be VA times this mass ratio, MA minus MB over MA plus MB. So this will be actually flip back. It will flip back if MA was less than MB, is less than 0 if MA is less than MB. So A will flip back. Otherwise, it will continue in that direction. If A was have bigger mass than B, then it's continue, right? And so, and this guy just becomes VB prime is equal to is PA. So I got a MA divided by MB. So I got divided by MB. So this one you will have to divide by MB, and so that's going to be VA. So incoming, and then you have a 2 times MB over total mass, big M total mass, and then that's just MB cancel this, and so VA, and this ratio is 2 MA over MA plus MB. So these are the answers you get when it's non-relativistic. Now, when you do relativistic, the answers are way more complicated, and you get more, much richer physics. Okay, so let's try to do that. I'm gonna leave this answer somewhere, and then I'm gonna work out how to think about this in a relativistic way, right? Okay, before we do the relativistic, you should see that I could have done this thing in center of mass frame, right? You can do this in this frame, and here there's a little bit symmetry here, where total momentum is 0. So this is total momentum 0, P total equal to 0, and so P total has to be equal to 0 also here. So, and so this would be px for us. And so in a vector way, if you want to have P total vector equal to 0 and P total vector equal to 0, so that defines the same frame. In this frame, that's the case. And so here we will know both UA and UB, just like we know VA and VB here. We will know the masses, and then we need to predict these guys, and it's really much easier. And maybe we should do this in a non-relativistic thing and see how easy or harder it is to do it in a center mass frame here. And then we're going to do the same stuff in relativistic. Okay, in the CM frame, so already we know it's going to be in this frame we have a far fewer unknowns, that MA UA prime, this is already the arrow is backward, so it should be equal to MB UB prime. I'm using U for it, and U and V's are related. You got to relate them in a non-relativistic way. So in the non-relativistic way, CM is going with some U, which is equal to minus UB. So these are related with each other. It used to be at rest. Now it's going to UB backward. So this will have to be equal to minus U. Just from the relation, and it's not so easy relation in the relativistic, but other things are not so easily related. But we will come back to the relatives. This is a relativistic situation. So I'm going to continue with this. So let's see what happens in CM prime. So this is, so if I know one, I know another. That's what I'm saying. It's really much easier to find. So that's one equation. So because momentum is 0 here, another equation will be kinetic energy here equal to kinetic energy there. So half MA UA square plus half MB UB square. So you already know UB is minus U, and okay, so let's see, so half MA UA prime square plus half MB UB prime square. So now it's, if I wanted to piece, it will be even easier. So this is equals to PA prime equals to PB prime, and so this is like a PA prime square over MA, and this is 2MA, PB prime square over 2MB, and this is total kinetic energy. Let's call it K in. Using now this in here, we will get a PA prime square over 2 1 over MA plus 1 over MB equals to K in. So PA prime equals to 2K in 1 over MA plus 1 over MB square root, and take a positive square root. And so I can simplify this. 2 MA MB K in over MA plus MB, and this is also equal to PB prime. So that's so PA prime in center of mass frame is this stuff. So we have to use kinetic energy and initial kinetic energy, and you gotta be able to have consistently these two will give you the same answer numerically in terms of once you transform. So the CM is going at U and B is going, this is equal to minus U. This must be equal to minus U because in the CM B is moving, but CM itself is moving with respect to lab. In the lab, B is at rest. Okay, so this is let's just write down the answer here. 2 MA MB K in over MA plus MB. Okay, so I hope I didn't make any kind of obvious calculation, some copying error, but this concept is similar. So in the center mass frame, things are usually very much simpler. Okay, let's see how the relativistic can work out in the lab frame. So when we do relativistic, we don't go out and write down expression for P and energy. Okay, so first thing I'm going to do is I'm going to set C equals to 1 for calculation. And this is a very standard thing, so you can later on you can always see so energy, it will be turned, it will like this, gamma m, and P equals to gamma m. If this is V, then V. Okay, so this will be at some speed, right? And this is rest mass. This is rest mass. So obviously MA is also rest mass. Yeah, these symbols. So later on, when we need to make sure that things are unitless and things like that, then gamma is going to be 1 over square root of 1 minus gamma of the V is 1, just this, because C is set equal to 1. Of course, this is unitful. This doesn't have units, so which means I need to put C down here if I'm looking at the C. So the V will end up in units of C. So that's the calculation. So like if you say V, if you do this thing and V turns out to be 0.2, that will mean V is actually 0.2 C. So that's the way we're gonna, when you use these units, you're gonna interpret later on. Okay, so let's do the lab frame. In the lab frame, what do we have? We have a P of A must be equal to P of A plus 0 must be equal to P of A prime plus P of P prime. So it's exactly the same equation as non-relativistic. I don't see symbol wise not that big difference. So instead of writing kinetic energy, we're going to write the energy of A equals to energy of A, but this one does not have zero energy anymore. So energy of A plus rest energy of B, which will be MA. So rest energy is, yeah, so energy of rest, gamma is 1, so that's just M0. So this is just MA, MB, I mean, MB, because this is at rest. That's equal to energy prime with this velocity, what the energy will be, to energy of B prime. So now we have in two different things. So remember that in non-relativistic, our calculation was kinetic energy was p square over 2m, right? In relativistic, this is not the case. You have E square equals to p square minus plus m square. So in the C, there have been C's in here. There used to be C square here and C to the power 4. So we have set C equals to 1. So we won't use them for the sake of simplicity. So you can now see that I can write I can do exactly same trick. So we can solve for E or solve for P. So this, we can try to write these guys as this is known because I know the speed, so I know these guys. So I need to know either convert this guy into P's or this guy into so let's call this the energy in. And so one of the ways, but there's a square relationship, so it's going to be some tricks involved here in calculation. So suppose I do this guy, I would say just like we did for the non-relativistic, we can say let's see PA minus PB prime equals to PA prime. Leave this on the other side and square this. What we're going to get? We're going to get a PA square minus 2PA PB prime plus PB prime square is equals to PA prime square. Okay, now PA prime square is E square minus M square is P square. So I can write this as EA prime square minus MA square, and this one will be EA square minus MA square. So we have a minus 2PA PB prime plus this one will be PB prime square. So now we see that this MA cancels from these sides, right? And we have so we want to kind of use this to eliminate the right hand side. So the right hand side is going to be EA plus MB minus EB prime square. So we have a EA square minus 2PA PB prime, and this guy is just EB prime square minus MB square, and on the right side I expand this guy out and get EA square. You can see you know, when I'm doing this relativistic cases, really nasty, lots of algebra, just too many terms to write. And there is a way to simplify it, and I know how to do it, but I'm just trying to not use that. It's called 4-vector notation. So to this with this and this with this to MB EB prime. So in here I have actually EA square gone away. So you have plus MB square, and that place is minus MB square, so we're going to add, and EB prime square go away. So there's only EB prime here, only so you have a EB prime is inside there, and AB prime is here, and AB prime is here. So if I send this guy on the other side and then square again, I should be in a good shape. Okay, so I went ahead and kind of did some more algebra and showed you how you can actually solve it. However, this whole thing is very nasty, and we saw in the non-relativistic case we should be doing these calculations center of mass frame, and then if we need to convert into lab frame, we just use what their conversion will be like. Okay, so I'm gonna not carry on and abandon this here, and we can just forget the lab frame, just do the calculation CM frame. And now I'm going to show you how the CM frame works. Okay, let's see some of these calculations in the center of mass frame. Okay, so even this calculation is not the right way of doing things. We will pretty soon introduce 4-vector notation, and when we do 4-vector notation, many of this algebra will become very trivial. Okay, and we can do a lot more with 4-vector notation, because once formulas become simpler, we can manipulate them so much more easily, right? Okay, but let's handle this. So we are in this center of mass frame. So first thing to notice is I'm going to do momentum conservation. So over here, PA, I'm going to write in the center of mass, PA in the center of mass, vector plus PB in the center of mass vector equal to 0. Now all along the x-axis, so this just basically means PA in magnitude equals to PB in magnitude. And similarly, P prime AC plus P prime BC equal to 0. This just means PBC, BAC is PBC. I'm using C to denote we are in the CM frame. Okay, these same symbols were used for the lab frame and can be confusing. Okay, so if I am going to find out energy conservation now, so energy conservation will be EAC plus EBC. So these are the incoming energies, so it's supposed to be known, right? So this is, I'm going to call E in. So this is the before, has to be after EAC prime plus BC prime. So we want to solve for these guys. Okay, maybe solve for this guy or this guy. These guys are known. Okay, so how do we do it? So we want to create another equation using these, and E square equals to P square plus M square, C equals to 1 unit, right? So in that we have that. So if you look at this guy, so this guy will just, this will become E in equals to, so this guy will be so I'm not going to use this directly, but just look at E, let's call it E prime AC square by itself is PAC prime square plus M square, MA square. MA is rest mass of A, that's my notation, and E prime BC square equals to P prime BC square plus MB square. Okay, so now P prime AC, this P prime is P prime BC. So if I subtract it, so this is equal to that. If I subtract it, this is going to cancel out. So E prime AC square minus E prime BC square is equal to MA square minus MB square. So this is like a plus B. I can use it here to get E prime AC minus E prime BC times E prime AC plus E prime BC equals to this right hand side. And now if I use this in here, I get E prime AC minus E prime BC equals to E MA square minus MB square over EN. So let's call this equation 2 and let's call this equation 1. From 1 and 2, immediately you get E prime AC is equal to, just add them, divide by 2. This is stuff. And E prime BC is equal to half 1 minus this stuff. And there you go. It's really quite trivial compared to what we are doing in the lab frame. Lab frame is a lot of work. To connecting lab frame to the CM frame and back and forth, it's much easier if you can understand some of the things that come with a 4 vector. And so that's what we're going to do. Next we're going to talk about doing these things using 4 vectors. And for some of you it may be a little bit more mathematical, but you know, that's the price of physics, because you want to do something more simply, you have to actually use a little bit better mathematics that's more suitable for that kind of concept. Okay, so 4 vector is more suitable for actually dealing with calculations in special relativity, and it's better to learn that and master it. Okay, take care. Bye.